Alrighty, awesome. So can everyone hear me and see me? I hope everyone can. So as Ryan said, I usually talk about the universe and simulating the universe on quite large scales. So I'm interested in how stars form. So this happens on parsec, light year scales of the universe. But today we're going to go way into the universe. We're going to zoom into much, much smaller scales, and we're going to try to understand the universe from an atomic point of view. It is a fact that the universe is made out of atoms. So it doesn't matter wherever you look in the universe, what you're looking at, you're going to run into atoms if you zoom in enough. So this is your coffee cup, this is your iPhone, this is the glass door, this is everything. If you zoom into it, it's made out of atoms. And because of this, we can talk about the general property of atoms and try to generalize our description of the universe for almost everything. So this is very, very cool. Just to get a general idea of essentially everything around us, we have to think about it from an atomic perspective. So I'm going to ask you a question now, because I know so many of the young stars are incredibly bright and going to be the future generation of the scientists in Australia. So I want to ask you, what do you know about atoms? So type in your answers now to the chat, and hopefully some of the answers that you give, I can use today to describe some of the things that we're talking about. And these are going to be things in your kitchen. These are going to be things, you know, just around the household. Atoms are small by Eric. Yes, atoms are small. That's exactly where I want to start too. Atoms are made of everything small. They're small. Yes, Libby. Atoms are particles made of quarks. Yes, indeed, our atoms are also made out of things. But today we're going to be focusing on atoms and not quarks. They are tiny. They have electrons. They are not indestructible. They are everything. Atoms are the small ones, very small. Electron, neutrons. What are leptons? Tiny. Okay, so that's enough. This is all excellent. This is all excellent. And it's exactly what I wanted to hear. Atoms are very tiny. So to actually understand, these atoms, we're going to have to develop some kind of atomic magnifying glass. So this is kind of just like a thought experiment, a theoretical physicist would call it. So we're going to first construct an atomic magnifying glass on our computers right now, and then we're going to apply it to a bunch of different things that we see around the house. So first we have to work out, as everyone has pointed out, atoms are very small, but just how small are they? So I'm going to have to give you some kind of scientific notation here. So we're not going to be doing any math, which for me is a bit unexciting because I love mathematics, but we're going to have to learn a little bit of scientific notation. And that is this kind of power that you can see here, 10 to the power of 2. So for example, here I have a ruler. Let's pretend like I've got a meter ruler, okay? And it's split into kind of 1 centimeter increments. You can see 0, 1, 2, 3, 4, 5. So there's 100 centimeters in a ruler. And the way that you can think about this is if I take a 1 meter ruler and I divide it by 10 and then 10 again, that's going to give me 1 centimeter. Instead of dividing it by 10 and then 10 again, I can divide it by 100 once, of course, because 10 times 10 is a 100. So in science, we use this shorthand notation to kind of illustrate 100, 10 to the power of 2. That is just 10 times 10. So if I divide my 1 meter ruler by 10 to the power of 2, I'm going to get 1 centimeter. And because I'm dividing by 10 to the power of 2, I can even use this shorthand notation, 10 to the power of negative 2. So this gives me an idea that I've divided something, in this case, my 1 meter ruler, by 10 twice, okay? So 1 centimeter, this distance here, really is dividing my 1 meter ruler by 10 twice. And we are going to keep doing this. We're going to keep dividing our 1 meter ruler until we hit the atomic scale. So let's keep dividing. So here I've zoomed into just this 1 centimeter now. I've just zoomed into this 1 centimeter and I've displayed it out onto this 10 measurements. So from here to here is now 1 centimeter, okay? From here to here. So that means from here to here, 0 to 1 now, is another division by 10 of our meter ruler. So that's 10 to the power of -3. So that means I've divided my meter ruler by 10, by 10, by 10 again. So 3 times. So that's 1,000th of my meter ruler. So I went from having this 1 meter ruler now divided by 10 into 10 increments, 10 increments again, 10 increments again. And now I'm at 10 to the -3. And we know this. We know what this is. This is a millimeter. This is a millimeter measurement. So we already know what that means, but we have to keep dividing. So even if we look on tiny little scales, 1 millimeter larger, that's not enough. We have to dive in deeper. So we have to keep doing it. We have to keep doing it like 5 more times, in fact. So we go 10 to the -5, we zoom in, we scale up, we divide again by 10, we divide again by 10, we divide again by 10. We get down to 10 to the 9, 10 to the -9. So that is, I've taken my 1 meter ruler and I've divided it by 1 billion, 1 billion. So that's 10, 9 times, okay? So this is the scale. These are the scales which we need our atomic magnifying glass to work if we want to see individual atoms. So these are the scales that are important. And you can see here, I've kind of drawn a line here where we actually start having to think about the universe in a completely different way. So as we zoom into the universe, the mathematical understanding of our universe changes into a quantum mechanical understanding. And I'm not going to talk about quantum mechanics too much today, but we will run into it a couple of times because it is very important for these scales in the universe. We simply cannot understand the universe without quantum mechanics at these scales. Okay. So we've developed our magnifying glass. Single atoms live here. So this is, of course, you know, we'll talk about this magnifying glass a number of the times during the talk. I'll bring it up again and again. And if you really want a really cool visualization, Google scale of the universe, and you can see zooming in and out of the universe at different scales, all the way past this atomic scale even. Okay, so extremely intelligent human beings, as we all are, we have engineered this kind of magnifying glass in real life. This one is an electron microscope. It's a special electron microscope. It was designed by the IBM people, the people who bring you amazing computers. And you can see here, these are actually individual atoms of carbon and oxygen that are being resolved and manipulated by this electron microscope. They've made this really funny stop motion video of this kind of, you know, this human being having a little dance while this atom jiggles around over here. So we have the engineering technology in the present to look on these scales for one, and also manipulate these scales as well. So this isn't completely theoretical craziness. We use these to engineer computers to change the reality around us. But of course, if I were to zoom into my desk right now, zoom into my computer, zoom into anything right now, it would not look like this. This is, you see, it's very clean. I can clearly look at this atom here on the left. It's, you know, I can see it right now. This is a highly controlled environment. This is done in a vacuum. This is a very special kind of electron microscope. The vacuum would be very tight. There would be no contamination from other gases coming into this and contaminating the surface. No, if we zoomed into anything, if we went to your kitchen right now and we zoomed in, it would look much more like this. So perhaps some of you play Minecraft. It actually looks much more like Minecraft, doesn't it? So there'll be many, many different species of atoms. So there'll be hydrogen, carbon, lots of nitrogen, I would say, oxygen, all interacting with each other as a big kind of atomic soup. And the surface would be rough and it would be irregular. It would be just a soup of chemistry interacting with each other, doing really interesting things. There would be nothing extremely regular at this kind of scale. So when we actually zoom into real things, they're going to look quite different from what we what we see in the laboratory video that I showed you previously. But there's something that every single thing will share in common. And it doesn't matter if I've zoomed into my coffee cup or if I've zoomed into my paper book or my phone, they're all going to share some similar characteristics. And these kind of things are the things that we study in physics and that we like so much about physics, is this explaining power across all these different things. So the two things that everything will share in common at these atomic scales, 10 to the -9, remember -9 means I've divided my meter ruler up into 10 increments, 9 times, so divided by 9, 10, 10, 10, 10, is the thermodynamics and the electrodynamics of these particles at these scales, these atoms, these molecules at these scales. So let me know, let me tell you what I mean by this, because thermodynamics and electrodynamics, these are really big words. And if you ever go to university and you study physics, you'll actually probably spend at least a year on each of these words, just trying to understand them properly, fundamentally, rigorously. We don't need all of that kind of understanding. We can kind of distill it down to some very basics, some very basic principles of these words. So instead of thermodynamics today, I'm going to talk to you about jiggling. We'll find out that jiggling is really associated with the temperatures of the materials, the temperatures of the atomic materials. And instead of electrodynamics, we can talk about attraction between different charges and repulsion between like charges. So you can see in these kind of simple simulations that I've made, there's lots of these molecules and they're all sticking to each other. So some of them stick together and it's when they have different charges, and some of them repel each other and it's when they have like charges. So really attraction and repulsion is governing the way things behave at these very, very tiny scales. And everything is always jiggling. So now that we know that at these very tiny scales, 10 to the -9 meters, so you know my meter ruler divided by 10, 9 times, everything is jiggling. And everything is either being attracted to each other or being repelled by each other, depending upon their charge. So using this knowledge, we can now go on an adventure. But before we truly go on an adventure, walk through our kitchen, understand various items, we should learn a little bit more about jiggling. So here I'm going to make a plot, and I haven't populated it yet. So I've got jiggling on the y-axis, and down here, so anywhere down here on the plot, there's not going to be much jiggling. So as I move up this axis, I'm getting more and more jiggling. So the atoms are going to be jiggling around more and more. And on the x-axis, or along the horizontal axis, I have temperature. So when I'm over here at this corner, I'm at very low temperatures. Indeed, this corner right here defines 0 temperature, and we will talk about that. And as I move across this plot, I increase the temperature until the temperature over here is very, very high. So what's the relationship between jiggling and temperature? Well, it ends up being like this. For low temperatures, really the atomic structure, whatever it is we're looking at, barely jiggles at all. And in some cases, it kind of forms this kind of, a lattice, you would call it, some kind of crystalline structure. And as we increase the temperature, as we go up, so we're moving across the temperature plot down here, as we increase the temperature, we increase the amount of random jiggles that these atoms have. And you can even see that probably in this plot, they're starting to kind of move around each other. They're not just jiggling like this, they're kind of moving around each other. It's almost like they're flowing around like a fluid. And as I increase the temperature even more, you can see that the jiggles are getting gigantic. These atoms are fully colliding with each other. They're coming apart. It's a fundamental relationship that we're looking at here, and it's all in terms of jiggling. So as the temperature increases, the jiggling increases. So I bet a lot of you straight away thought, well, yes, of course this is true. I know it's the case because I've seen water before. And yes, you're right. This is very analogous to a system like water. Essentially, somewhere in the middle, the temperature will be just good enough so that the atoms can just kind of flow around each other. They don't, you know, they're not jiggling hard enough to bump each other away, but they're just kind of all staying together, jiggling around, happy family. But then when you put your water in the freezer, you're removing that jiggling. The refrigeration device extracts jiggling from things. And essentially it removes the jiggling until they kind of just all fall into this state where they form a crystalline lattice like this. And we call that crystalline lattice ice. On the other hand, as you increase the jiggling, as we will do soon, essentially what you're doing is pumping it full of energy. You're making these jiggles very large and the atoms kind of collide with each other. They're even becoming less dense. You can see that there's less atoms in a given piece of area up here. So you're creating steam here. The atoms are free to go wherever they want. You're creating steam when you increase the amount of jiggles. So the larger the jiggles, the hotter the object. This is the key takeaway. We can understand the universe at this scale through jiggling. So something that I should have pointed out, it seems to suggest that on this graph that when there's no jiggles, when there's absolutely no jiggles in the system, the temperature is 0. Probably some of you know about this as the absolute 0 temperature. And this can actually not exist. And why can't this exist? Well, here is a simulation, not one of my simulations, but a very good simulation of nothing. So this is what happens when you simulate absolutely nothing. There's no particles in here. There's nothing. It's a complete vacuum. And what you see, because of quantum mechanics, because of something called the uncertainty principle, is that pockets of energy will pop in and out of existence. And this kind of, you see that I would call it the density of the energy is kind of the color here. So when it's red, it's very energetic, and that energy has jiggling associated with it. So you can just put a bunch of atoms in a vacuum, and they'll just always be jiggling no matter what, just because these quantum fluctuations will be happening everywhere. They're happening everywhere in the universe. We can't get rid of them. So the universe is always jiggling. We'll never get to absolute 0 without experiments because of this quantum fluctuation always happening in the background. Okay, so that was kind of, there's a lot of stuff going on there. We just learned that jiggling seems fundamental and we can never get rid of it. And we talked a lot about, well, not a lot, but we talked a little bit about quantum mechanics. Now, this seems kind of abstract, right? We're talking about quantum mechanics, we're talking about jiggling atoms. And we know that this applies to everywhere in the universe, but we also know that our kitchen is in the universe. So of course this applies to everything in our kitchen. So let's try to understand some things from our kitchen with this understanding of jiggling. Okay, so here I have a kettle. I have a heat source right here. So I think modern kettles have the heat source built into them, but let's pretend that, you know, we're putting our kettle on the stovetop or something like that. And then I have a bunch of water in here. Of course, we want to boil some water. We want to make some tea. That's maybe some of you don't drink tea, but maybe we want to make a hot Milo or something like that. Then we have a power source. So, what do you think will happen when I turn this kettle on? Let's open this up in the chat. What do you think will happen when I turn this kettle on? So I've got the power here. I'm going to turn my kettle on. What do you think is going to happen? The water will boil, it will boil. Yeah, the water will jiggle more. The water will boil. Jiggling. Yes, start to jiggle. There will be lots, yes, heating up will create more jiggle. Oh, I like this. The water will turn to steam. Yes, exactly. Atoms will come. Oh, awesome. Steam, atoms will jiggle. This is perfect. Okay. Yes, awesome. Thanks for all the great responses, everyone. Okay, that's exactly right. So now I've turned my kettle on and we see a lot of jiggling occurring. So, oh, this is pretty cool. So look at this. So essentially the heat source is down the bottom here. So realistically, it should start jiggling more and more down the bottom and it'll slowly work its way up to the top. And of course, the atoms that are all along, or they're not atoms actually, these are molecules. This is H2O, this is water, one oxygen and 2 hydrogen atoms joined together. But the molecules all along this layer up here don't really have anyone else to jiggle into. So they're going to really be shoved off the end and form steam much more easier than any of the molecules down here. So we also always see this kind of surface layer effect where these atoms can get bumped off really easily. And indeed, that's what evaporation is. Evaporation will happen because some atom coming from the air will come down and smack into an atom on the surface and it'll bounce it off. So it'll slowly evaporate. But yes, we can see that we increase the energy down here. We increase the heat down here, the temperature, and we create these jiggles, and the jiggles propagate all through the system and they end up causing steam coming out of the top of the kettle. So after a while, this whole system will be, you know, boiling, and then we'll take it off and we'll make our tea. But something that we have forgotten in this whole picture is that everything is jiggling. Everything is made out of atoms. This kettle is not a solid kettle made out of nothing. It is made out of atoms. And that means everything is jiggling here. And this is where very important engineering techniques come in. So essentially, the actual heat source here is converting electricity to jiggles. So you have to create a material that is able to efficiently turn electricity into jiggles. Then the jiggles can propagate through the kettle, can boil our water. But the kettle itself, the material that makes up the kettle, is also jiggling. And of course you can feel that because you can put your hands close to the kettle, not too close because you don't want to burn yourself, and you can feel the kettle itself is warm. So this is jiggles that are going into heating up the kettle rather than heating up the water inside the kettle. So we would like to minimize that, and the engineers will come up with excellent materials that will not conduct heat very well. So the kettle hopefully won't boil with the water. So yes, everything is jiggling. Okay, so let's move on. We just made some tea. So maybe it's around breakfast time, I guess. So now we should cook an egg as well. So here I've got another very simple diagram. You'll learn that physicists are excellent at making really simple diagrams. And let's add an egg. So there, we'll chuck an egg in the pan. Okay, so I guess we should turn it on. And of course that means upping up the amount of jiggles in my stovetop. So my stovetop was just sitting there jiggling, kind of, you know, pretty relaxed. And I pumped electricity through it and it starts jiggling a lot more. So then the pan starts jiggling, of course. So it's transferring jiggles to the egg and it cooks the egg. So when I say cooks the egg, I mean, what do I really mean? Of course, one thing that we can visually see, and you can see it happening right now, is that my egg is going, the egg white is going from clear to white. So I want to quickly throw it to everyone out there. What do you think is actually happening here? So my egg is going from clear to white as I cook the egg. So what is this in terms of the atoms jiggling the egg? What makes them go from clear to white? So let's open up the chat again. Let's get some ideas. Removing water. Oh, that's a good idea. Yeah, it could be evaporating water. Some people don't know. That's excellent because that's why I'm here giving this talk. People say, yay, the heat, the protein. Oh, someone said the proteins are tangling. That is an excellent idea. Heat hardens the egg. Okay, making it burn. Don't know. The gel in the egg is white turn to. Ooh. Anyway, excellent, excellent, excellent. So lots and lots of great ideas. So I think we have to get our atomic microscope here and probe into what's happening. Okay, so essentially the egg is made out of these things called proteins. And proteins are the building blocks for essentially everything that's alive. So proteins have many, many different roles in your body, in not only my body, but your body, everyone's body. And in the egg, there's this protein called albumin. And albumin is kind of really rolled up. It's really scrunched up, okay? So of course, these proteins are made out of atoms because everything in the universe is made out of atoms, but it's all kind of scrunched up really tightly into a ball. And when the light from, from your room, the sun, anything comes in, it can't actually interact with these proteins because it's so scrunched up. It just passes through them and reflects off the pan, comes back to your eye, and you just see it as being clear. But as we introduce more and more jiggling, the atoms in these proteins are jiggling around and they become unwound and they turn into more like these kind of ribbons here. So these long ribbons. And once they become long enough, the light actually starts interacting with them. And instead of going straight through the egg white, it bounces off the egg white, returns to your eye, and you see it as being white. So the jiggling unravels these scrunched up proteins into it. The whole process is called denaturing. It's denaturing the proteins. It's unraveling them so they become larger structures and light can interact with it. And then we see it as the egg white becoming white. So we can understand how the egg is cooking based upon the atomic physics of jiggling. So that's the takeaway here. That's why it's fun cooking eggs. Okay. But what about if we don't cook with an electric stovetop? We start cooking with something that is really cool, fire. So very, very similar kind of deal, right? Somehow the fire, we all know fire, it's hot. There must be lots of jiggling particles all around the fire. If we were to cook with it, it would heat up the pan would jiggle, and then our food would be jiggling, denaturing proteins, removing all the bacteria from the food, making it edible, making it easier to eat. So that's the whole point of cooking things. But what is happening down here? So what is happening with this fire at an atomic level? And I've decided that I'm not going to talk about this right now. I want you guys to talk about it with, whoever in your house. And I want you to tell us some of your thoughts about this, either on our Facebook page, via email. I want you to think about this. What could be happening at an atomic scale to produce fire? Now, of course, fires need a source, so they have to have these logs. They have to be burning logs, and they need kind of oxygen. They need to take in gas, and they need to somehow combine the gas from the air and the logs together to create a heat source and also a light source. So the fire is actually producing light as well as heat. So it makes it a bit complicated, but I just love hearing your ideas about these things ever since I asked you about how stars form last time I gave a talk. So yeah, please send us your ideas. That would be excellent. And I'll do a follow-up video next week describing, what is actually happening here. But I really want you to think about this before I tell you, because it's just fun to think about things like this. Okay, so essentially, we have just learned that no matter where we look at the small scale universe, so when we take the meter rule and we divide it by 10, 9 times, everything is jiggling. And that's because it can't not be jiggling because of quantum mechanics to start off with, and everything has some kind of temperature. So any kind of thing with a temperature will be jiggling about. So that's what we've kind of learned here. We can describe things in the kitchen with jiggling. We can describe cooking with jiggling, heating up our water, boiling our water with jiggling. Jiggling seems to be quite fundamental at these very, very small scales. But what about the large scale universe? So instead of going 10 to the negative 9, which means I divided my ruler a billion times, let's go the other direction. So let's multiply the ruler, 1 meter ruler, by a billion. And when I do that, I get to scales in the universe, roughly the same size as the sun. So this is what it kind of looks like on the other side of the same kind of coin. At 10 to the negative 9, we have atoms. Then we have us somewhere in the middle. And then at 10 to the 9, so when we multiply it by a billion, we have the sun. This to me is not actually the large scale universe. The sun is actually a very small thing in the universe. So we have to go to even larger scales. And wow, the sun is beautiful, by the way. This is a video from NASA that just came out, I think it was 5 days ago. And I'm pretty sure it's 10 years, a decade of the sun. And they've taken a snapshot each day, I'm pretty sure. It's amazing. You guys have to go watch that. Go to the NASA website and check out that video. But yes, we need to go bigger. So this is not the large scale universe. I want to go way bigger. So now I've gone to 10 to the 21. So that's, I take my ruler and I multiply it by 10, 21 times. It's huge. It's huge. And what happens at this scale? Well, something amazing happens, because where we had all this jiggling on small scales, we start seeing the same thing happen again. But instead of jiggling atoms, we see jiggling stars. So right now you're seeing a simulation here. Each point particle, a tiny little particle, a tiny little jiggling dot in here, which is jiggling around, is an entire star. And we not only do we find this amazing because it's an entire star, but these stars come together under the action of gravity now. So no longer before, where we talk about attraction and repulsion from electrodynamics. Now it is simply gravity, which is an attractive force, bringing together all of these jiggling particles, which are entire stars, forming entire galaxies now. So all of these stars are coming together, jiggling under these kind of turbulent, kind of random motions, and being attracted to each other through gravity and forming entire galaxy systems. So we've just found something fundamental about the universe, that it seems to be similar on scales 10 to the -9 as it is on scales 10 to the 21. Of course, there is some differences because gravity only attracts things. So it's only pulling towards each other things with masses. So it's only attracting things. There's not the repulsion, but still we fundamentally see jiggling is a fundamental across the universe. And this is kind of where I'm going to end the talk today. So jiggling is universal. Thanks very much, everyone.